In this video, we're going to be going over the basic idea behind set theory. So we're going to start off with a little bit of notation. So if the element x is in the set A, then we denote this by writing x in A. If each element in A is also in B, then we say that A is a subset of B. And this symbol means subset. If A has nothing in it, so there's no elements, then that means A is equal to the null set. So this means the null set. Now we're going to be going over two kinds of operations that are used on sets, which is the union and also the intersection. So we're going to start off with the union. Union is what we normally call the OR operator. And it's called the OR operator because it's the set of all elements that are in A or B or both. So in other words, it's at least in A or B. So if we look at a Venn diagram here, the union would be represented as A union B, which is all of A, all of B, and of course, what's both of them also. So a few kinds of properties of unions is if we have A unioned with the null set, so we're adding nothing to A, then of course all we're left with is A. If we put together A unioned with A, then we're still left with just A. And here, if we have a sequence of different sets, A1, A2, all the way up to AK, and we have unions between all of them, then this can be denoted as the union where I equals 1 to K of AI. So this is just a notation. Now we can also look at intersections. Intersections are what we usually call the AND operator. It's the AND operator because it's the set of all elements that are in A and that are in B. So this is represented as A intersect B. And on a Venn diagram, this refers to the middle portion, the elements that are in both A and B. So now if we have A intersect with the null set, well, the only thing in common between A and the null set is nothing. So the intersection is the null set. A intersect with A is of course just A. And similarly, if we have a sequence of sets A1, A2 up to AK and we're intersecting them all together, we can denote this by writing the intersection from I equals 1 to K of AI. Now we also have the distributive law in sets. So what this means is if we have on one hand A union B and we're intersecting that with C, we can distribute the C across the union. So that would look something like this. We would have A intersecting with C, and then that's unioned with B intersecting with C. So we've distributed the C across. Similarly, if we have A intersect B, and that's unioned with C, then we distribute the C across the intersection this time. So A union C intersect with B union C. So this distributive law is helpful in a variety of applications. One of them is if we're trying to visualize a set notation. So here we have two examples which are the same as the distributive law. We have in the first case A union B intersecting with C. So there's two different ways that you can look at this. You can just look at it as it's written and consider, well, what's A union B? A union B is this whole portion. This is A union B. And C is this. So what's in common between them? It must be just this part. You can also look at it by the distributive law. As we set up here, A union B intersect with C is A intersects C, A intersects C. So what's common between A and C? That's this portion. And then we have B intersects C. That's this portion. And then if we're putting those together, then we're left with the same result, is this portion. So A union B intersecting with C is this portion. Now we can look at the other example, A intersect B unioned with C. Again, we can look at this in two different ways. We can just look at it as it's written. So we have A intersect B. That refers to what's common between them, so that's this part. And then we have C, which is of course this part, and we're joining all of those areas together because this is a union, so it becomes all of this. We can also look at this by the distributive law, because we have A intersect B unioned with C, so that's A union C, B union C, and the intersection between those two. So A union C is this whole area, A union C. B union C is this area. And then where do they intersect? They intersect all here. So that's this whole area. So now something to also note here is the entire space, so everything that's possible to happen is noted by this C. So the entire space is C. Everything in that space that's not part of a specific set A is what we call the complement of A. And that's written as AC. So this means that if we were to put together A unioned with AC, a complement, so we have everything that's in set A, and we're also adding to that everything that's not in A, then of course all we're left with is the entire set, the entire space rather. Similarly, if we look at A intersect with AC, well, if A complement is everything that's not A, then there is nothing between those two that are common. So that means the intersection here is the null set. And here we see that complements sort of cancel each other out. So if we start with A complement, and then we're looking at the complement of that, then we're undoing that, and we're ending up just with A. Now we also have something here called De Morgan's laws, and these are helpful when we're trying to break apart different sets or try to understand different questions. So if we have the intersection of A and B, and we're looking at the complement of that unit, we can break this down and say that this is equal to A complement unioned with B complement. So it's helping us to distribute that complement across the intersection. Similarly, if we have A unioned with B and the complement of that, then this would be A complement intersect with B complement. Finally, in this video, we're going to be looking at probability set functions. So this is the idea of the whole time before we were looking at just sets. So now we're bringing in the probability notion into this. What's the probability of A happening, of something happening? So of course, this is what we write, the probability of A. Now here it looks simple, but of course A could be a whole complicated sets. It could be a lot of different things. So this is just saying the probability of something called A happening. So there's a few properties of these set functions, these probability set functions. So the first thing is that the probability of something happening is greater or equal to 0, and it's less than or equal to 1. So this means you can't have negative probabilities, and you also can't have a probability greater than 1. You can't have something that has a probability of 2, for example. That doesn't make sense in this context. The probability of A complement is simply 1 minus the probability of A. And following this, the probability of the entire space, so the probability that something happens, whether it's A or not A, or whatever it is, this is certain to happen. Something is going to happen, or nothing will happen. But the point is, within the space, some event is true. So the probability of the space is 1, and the probability of nothing, of the null set, is 0. We also have for subsets, if A is a subset of B, then this must mean that the probability of A happening is less than or equal to the probability of B. So they could be the same, but they have to be at least the same or less than. The probability of A has to be less than or equal to the probability of B if A is a subset of B. Finally, we have this important relationship which helps us understand what the union between A and B is. And it's helpful to see this by looking at a Venn diagram. So if we start off with, what is A union B? What is A union B? So on a Venn diagram, A union B is this entire area, A put together with B. So what is this equal to? So we can start with saying that, okay, the probability of A union B is the probability of A. So the probability of A is this whole portion. And we will add to that the probability of B. So that's this whole portion. Now, if we leave it like this, what we've done is we've double counted the intersection, this part in between, because this was counted already of the probability of A, and it's again counted with the probability of B. So we have to subtract that intersection once, because we only want to count it once. We don't want to count it twice. So this blue area here, we're going to subtract that. So this is the probability of A intersect B.